Make LLM output repeatable every time in Python. By the end, you will have a tiny deterministic generation pipeline. You will see how a seed, temperature, and a simple cache give repeatable, explainable outputs. You will also learn how batching keeps runs fast and stable. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced in simple Python. Deterministic runs solve a practical pain. When you debug prompts, evaluate systems, or reproduce experiments, you want the same output each time. Otherwise, tracking changes feels impossible. The alternative is a fully stochastic model where tiny randomness hides bugs but can help creativity. Deterministic control trades a bit of diversity for repeatability, which is what you want for testing, A/B evaluation, and unit-style checks. It also keeps latency predictable for small experiments. Think of it like a dice with painted sides. A seed picks which side is visible given a prompt. Temperature decides whether you always show the highest face or sometimes let lower faces appear. Caching remembers previous roles, so repeated questions return instantly. This balances consistency, controlled randomness, and speed. We will build a pipeline that picks tokens deterministically using a seed, applies temperature to shape probabilities, caches results for repeat runs, and batches prompts to reuse the cache. Now we'll implement the deterministic token selection. This snippet selects a deterministic mock LLM token using a seed and prompt. It shows how a seed initializes a random generator, so the same prompt and seed give the same token each run. The snippet uses the prompt text and the seed together to make a reproducible selection. So changing the seed or changing the prompt will change the chosen token. If you pick a different seed, the whole sequence shifts, which is useful for testing different stable behaviors. This pattern gives a clear baseline to compare later temperature and caching effects. Next, we'll add temperature to influence choices. This code applies temperature to scores and returns the highest probability token after scaling. It converts raw token scores into a softness controlled by temperature, where a low temperature sharpens the highest score and a high temperature flattens scores, so less likely tokens gain chance. The snippet then picks the top token after that scaling, which demonstrates the practical effect. Small temperature values produce near deterministic outputs, while larger values add variety. When tuning temperature, lower values improve repeatability and reduce surprise, and higher values increase diversity at the cost of consistency. Now we'll compute a probability ranking that temperature can reshape. This example computes a temperature-scaled probability ranking over tokens by applying softmax, which turns scores into probabilities. After dividing scores by temperature, it shows how temperature acts as a gain control. Heat raises probabilities of lower scoring tokens, while cold makes the top candidate dominate. The code ranks tokens, so you can inspect the distribution, not just the winner. Watching the ranked probabilities helps you decide the right temperature for your use case, since you can observe whether the top token truly dominates or if alternatives carry meaningful mass. Next, we'll make results fast and repeatable across runs with a cache. This snippet caches deterministic generations to make repeated runs identical and fast by storing outputs keyed by the prompt and seed. On a cache hit, the system returns the stored token and avoids recomputation, cutting latency on repeat queries. The example highlights cache key design. Include seed and relevant prompt fields to avoid accidental collisions. It also shows a simple eviction note because an ever-growing cache can consume memory. Using a disk-backed cache or an LRU policy is the next step when you move beyond toy experiments and need long-running stability. Finally, we'll batch prompts and reuse the cache for throughput. This code batches prompts, reuses the cache, and shows stable, unique outputs across a batch by looking up each prompt seed pair and computing only the misses. Batching reduces overhead when you have many short prompts and makes effective use of vectorized or bulk scoring logic. The example reports how many cache hits versus misses occurred and prints stable outputs so you can confirm repeatability. Batch size influences latency and throughput. Larger batches improve throughput but increase per-item latency and memory use, while smaller batches keep per-prompt latency low. Recap: deterministic LLM runs use a seed to fix randomness, temperature to control diversity, and a cache to make repeated runs fast and identical. Use this approach when you need reproducible debugging, reliable evaluation, or deterministic A/B tests. One caveat: overdeterminism can hide real-world variability and reduce creative outputs. So keep a path to controlled randomness for final production tuning. Next step, scale this pipeline to a larger prompt set, measure timing and stability, and add a persistent cache or approximate indexing if you need higher throughput. If practical AI engineering helps you, subscribe and watch the AI engineering videos.